About now? You see now?
Yes. Yeah. Please go ahead.
You see now my
Yes, we can.
right.
Please go ahead.
Right. So we've been working over the last over the years on laser uh, the use of laser technologies for the production of carbon nanomaterials. We did some pioneering work in the 90s on the production of single-wall carbon nanotubes by laser ablation. We were actually the first group in Europe that produced carbon nanotubes by laser ablation back in the 90s. And laser technologies have been used for the production of other carbon nanomaterials like carbon nanofoams, carbon nanohorns, or shell-shaped carbon nanospheres, like the ones we are showing here. And so one day in the lab, we were working for a company that was interested in making gold coatings on ceramic tiles. So what we did is just, we deposited a thick layer of gold salt precursor, which is organometallic gold complex. And we radiated it with continuous wave neodymium jack laser. And we observed the formation of this kind of soot, which is like a spider web soot, that with this one resembled very much the texture of the soot we produced when we were producing carbon nanotubes. So we were excited because we were producing carbon nanotubes in air instead of, just working under argon or protective atmospheres. And we were using a molecular precursor, which was very interesting, instead of a hydrocarbon or gas or graphite, like we did with carbon nanotubes. So when we did electron microscopy characterization, we observed we produced this kind of a spongy-like material. And when we did TEM, we observed this material actually consisted of embedded within carbon matrices. So it was not carbon nanotubes, it was a different material. And because of this spongy-like texture, we decided to call this material gold carbon foams or gold carbon nanofoams. So we thought this we expected at the beginning that we were going to a thermal process, so we would burn all the organic moiety would be burnt, but instead we got the formation of soot. And this is because this is a laser-induced mechanism where there's cluster recombination of very reactive species in the generated plasma plume. So we got the production of this kind of soot, which is common for many kinds of laser ablation synthesis methods. So what we want to show in this work is that we can control the synthesis of our carbon foams by laser ablation of different precursors. In particular, want to see if we can, by changing the ligand type and metal of the used organometallic complexes, we can change the composition, the structure, and therefore the properties of the produced materials. And we will design physicochemical processing routes so we can use these carbon nanofoams for different applications. So we started working with gold organometallic compounds based on phosphines, but we wanted to extend this work to other kind of organometallic compounds with other ligands and metals. And we realized that all these materials had this kind resulted when doing the laser ablation of these organometallic complexes. In all cases, we obtained different kind of metal carbon forms, so we can change the metal composition by changing the composition of the metal of the organometallic complex that was irradiated by laser. And then we could change we could use the ligands, the organic ligands, as carbon feedstock for the production of these carbon foams. If you had stereo glasses like these ones, you could see that these materials are really spongy, and they have this kind of a remarkable and beautiful spongy-like structure, or foamy-like texture, which is really cool. A very careful TEM characterization of these materials revealed that these materials are actually a composite of three separate components. So we have, first of all, we have metal nanoparticles embedded within amorphous carbon matrices. We have amorphous carbon aggregates and multi-layered graphitic nanostructures. And this is very interesting because they are not mixed all together. You could actually see that they are, eventually you can see that they are separate components in these materials. So we realized when we did XRD studies as well as thermogravimetric studies to measure the carbon content, the metal content, and the metal nanoparticle size. And we realized by changing the metal and the ligands, we can and the organic moieties, we can change the particle size and the carbon content of these metal carbon foams. So is it possible tuning the composition and structure, and therefore the properties of the metal carbon foams, by suitably choosing the irradiated precursors? What we did is we did a systematic study just using different gold phosphines. So we used non-aromatic gold phosphines as well as aromatic gold phosphines. So we increased the aromaticity or the aromatic content and carbon content of our precursors. And we wanted to see if we can control the structure and composition of the resulting carbon foams by just adjusting the composition of the irradiated precursors. And what we observed is that these materials, they all looked very different. When we irradiated aliphatic gold phosphines, we observed large metal nanoparticles with very low carbon contents, as you can see here and here. Whereas when we increase the aromatic content of the ligands in these precursors, we increase the carbon content of the carbon foams. So the average crystallite size decreased when increasing the number of aromatic moieties and the carbon content of the irradiated targets. And the metal loading decreases when increasing the number of aromatic, you can see by increasing the number of aromatic moieties, the metal loading decreases. Or when using aliphatic moieties, the metal loading increases. We also got some other interesting and exciting results by using this kind of tetraphenyl porphyrin, and by using this triphenylphosphine derivative. And we got different results in these cases. In one case, we got the formation. This is different material, graphitic hollow spheres, which were not so evident from in the other materials. And very interestingly, by irradiating this precursor, we obtained single-wall carbon nanotubes. When you can imagine, we did pioneering work on carbon nanotube production. So these kind of results are really excited that we get more ordered carbon nanostructure growth in also by doing this kind of experiments. We characterized by Raman spectroscopy these carbon nanotubes, and we observed that by irradiating with a red laser or a green laser, when we irradiated with the green laser, we obtained the typical response signal of semiconducting nanotubes. When exciting with the red laser, we obtained the Raman resonance of metallic nanotubes, and because you can see differences in the profiles in the bright big Nerfano bands. And if we analyze the radial breathing modes, we observe that the more intense peaks bands are around 1.4 and 1.44 nanometers. And we can get also very narrow distribution, diameter distributions, which is very interesting. So it is like interesting that we can control the diameter of the carbon nanotubes by just using a molecular precursor. So it can be interesting for controlled carbon nanotube growth, this laser ablation approach. We identified that we have identified specific metallic and semiconducting nanotubes, and these are all possible carbon nanotubes, and you can see how close in diameter they are. And among all possible nanotubes, we identified two different single-wall carbon nanotubes which are almost identical in diameter, and this is, I think, a remarkable result. We wanted to know more about the role of metals in the growth of graphitic structures in the carbon forms. So we radiated different commercial organic compounds, polyaromatic compounds mainly, and we observed that all of these materials resulted in the production of this kind of foam-like nanomaterials. And in these materials consisted of amorphous carbon aggregates and ordered graphitic concentric structures. So metals are not involved in the growth of these graphitic nanostructures. And very interestingly, when we radiated triphenylphosphine that we used in our previous work, in our initial carbon foam studies, phosphorus is only detected in amorphous carbon nanoparticles in metal-free carbon foam synthesized from triphenylphosphine. So graphitic structures might result of amorphous carbon restructuring and phosphorus removal. So you can see phosphorus is not present in in EDS studies of the graphitic nanostructures observed in these metal-free carbon foams. We did several physicochemical characterization studies. We got disappointingly low surface area values, but these materials are pretty stable under air atmosphere in thermogravimetric studies. And very interestingly, our carbon foams disperse very well in water and many other solvents like acetone, ethanol, or toluene. So this is interesting and provides new processing opportunities for our materials. For example, we managed to disperse in water our carbon foams with the help of sodium alginate, and then we coagulated them, these dispersions in sodium chloride, in calcium chloride coagulation baths. So we got the production of fibers. So we spun fibers of our carbon foams, which is like cool. It's a kind of cool result. We also performed some other kind of physicochemical characterization studies on mainly on palladium and platinum containing carbon foams. And we observed, these results are really preliminary, so we have to be cautious about them. We observed this kind of ferromagnetic behavior. Also, we did some electrochemical characterization of metal-free carbon foams, and we observed that when thermally annealed, we can get an increase in electrical conductivity and in capacitance of these materials. We also studied our carbon foams as supports for in catalysis, in particular for the phenylacetylene hydroamination with aniline that requires gold nanoparticles catalysts. We initially tried to do these catalysis experiments with our gold carbon foams materials, but our gold nanoparticles are all coated with carbon layers that prevent the interaction between the gold nanoparticles and the reactants. So it doesn't fall. So for these materials, the catalysis does not work. However, we decided to try another approach. It's just decorating metal-free carbon foams with gold nanoparticles by just reduction of chloroauric acid with sodium citrate, by reduction of chloroauric acid with sodium chloride and sodium borohydride. So we got our metal-free carbon foams very well coated with gold nanoparticles. And for comparison studies, we did the same studies with several other carbon nanomaterials as carbon supports, including carbon nanotubes, single wall to multiple nanotubes, nanodiamonds, carbon black, graphene oxide, graphite, graphitic cones, or this kind of other mesoporous carbon, activated carbon. So we tried all these carbon materials for as supports, and they all were coated well with gold nanoparticles. And by adjusting the gold carbon ratio for all these materials, we got successful results in terms of conversion of or catalytic activity for the hydroamination reaction. In particular, it worked pretty well for graphene oxide and for all materials with high surface area and good dispersibility in water and well-developed mesoporosity. And this is the case of our carbon foams, which provided conversion values which are comparable to the conversion values of other materials like graphitic cones or carbon gels or nanodiamonds. So we got nice, like compatible, or let's say, we got nice results with our gold nanoparticle decorated carbon foams. And finally, I'm going to show you some more of our latest results on carbon foam production with with just by laser ablation, but instead of using organometallic complexes, this time we tried a different substrate, which is graphene oxide. So we radiated graphene oxide and we observed the formation of this kind of foamy material, foam-like material. And these are TEM images that show this rosary-like assembly of these very tiny nanoparticles of carbon foams, carbon aerogels. Eventually, you can see graphene oxide platelets that were ejected during the laser ablation process. These materials exhibit very poor stability and poor substrate adhesion. But if we immerse them in water, and when we take them out again with another substrate, this material becomes more dense, and capillary forces induces compressive stress, which makes this material more easier to, let's say, easier to handle and to manipulate. And this material actually presents nice conductivity and nice capacitance. So we can, by doing this water transfer process, we increased the capacitance of these materials from 17 to 42 farads per gram. And these materials, if deposited on interdigitated electrodes, can provide remarkable nitrogen oxide, NO2 sensor capabilities. So this is like interesting because we observed that we can get very low detection limit below 10 parts per billion and remarkable selectivity among, with other, let's say, very remarkable selectivity when compared with other contaminants, pollutants. So you can see for NO2, it works pretty well. It's a very good sensor, and sensor is works better if in humid environments. So this is very interesting for, so it makes them really applicable for real world measurements. And there's a novel sensing mechanism is proposed for these materials to explain this very nice behavior in humid environments. And it's based on the enhanced solubility and reactivity of NO2 in a water layer which is surrounding this foam material, because these foam materials have hydrophilic functional groups like hydroxy and carboxyl groups. But so there's always a very thin water layer surrounding them that favors the solution of NO2 and its reactivities. That's the reason why it works so well. And actually, the performance of this sensor is comparable and also competitive with other materials that are being used in sensor technologies. So conclusions are laser chemistry approach is very versatile method for tailored synthesis of metal carbon nanomaterials, nanofoam materials, and we can produce a plethora of metal carbon nanohybrids and and we can control, by controlling the chemical structure of the ablated precursor, we can control the structure and properties of the materials that are synthesized. Despite the low surface area, the good dispersibility and mesoporous nature of our carbon foams allows efficient use of metal-free carbon foams as catalyst supports, and we can get a good let's say competitive NO2 gas sensors, chemisensors, using these laser deposited carbon foams derived from the laser ablation of graphene oxide. I would like to acknowledge my collaborators and this conference organizers, and I would like to dedicate this presentation to the late professors Victor Herrera and Rafael Navarro, who pioneered the nanotechnology studies here in my hometown of Zaragoza, Spain. And thank you for your attention.
Thank you so much, sir. Thank you so much for your presentation. It was a wonderful presentation. If anyone have any questions or comments, you can please ask, Professor.
Good morning. Marina Schwan is here from Germany. I have a question regarding the carbon aerogels. Do you think there is a possibility to scale up this synthesis, or maybe you can comment on the sample size on carbon aerogels?
Oh, that's an issue. Yes, that's an issue. We produce the production of the production is not competitive in terms of the amount of materials that are being produced, and this is a serious drawback actually. And even in the case of this last, when using organic precursors like triphonyl phosphine or naphthalene, of all those materials, the production is even if we use cheap precursors, cheap molecular precursors, the yield is really low because most of the material melts or just produces like vapors, which are dangerous or toxic, let's say toxic, and the yield in terms of amount of material that are being produced during these processes is really low, and this is an issue. So we can compete against, for example, carbon aerogels produced from resorcinol or other chemical routes, or that soft chemistry routes that can produce, let's say, kilograms of aerogels very easily. And this is a completely different approach, and we can compete against in terms of the amount of material that is being produced.
Thank you, Professor.
Thank you, Marie, for your question.